Let's start. Yesterday we have learned the equipment circuit. Today we learn the torque equation of the induction machine. The torque equation is also important to know the IC induction machine. We usually use Thevenin equivalent circuit to calculate the circuit. Thevenin equivalent circuit. Thevenin. It can simplify the calculation of a complicated circuit, such as viewed from the two terminals A and B. Viewed from A and B. The whole circuit can be seen where it is a single voltage source VEQ in series with impedance ZEQ. So this complicated circuit turn into this simplified circuit. So this is the Thevenin theorem. So in this circuit, there are only one source and only one impedance. So the form is simple, and it can help us to calculate the parameters of the circuit.
Already done RC.
RC is omitted. Omitted here. Generally omitted. It's not the REE. So here, just we don't use. If you use RC, is okay. Okay. We can also calculate the impedance, the equivalent impedance. Let's see these two equations. The voltage, the equivalent voltage and the equivalent impedance can be calculated by these two equations. Just use this figure just in parallel and in series. We have mentioned it yesterday how to calculate the equivalent impedance. So it's easy to obtain these two equations. It should be noted that if when we want to calculate the the ZEQ, the impedance, if you want to calculate the impedance, here the voltage source should be shortened, just set equal to 0. Set this point to this point, just you see as a line, the resistance 0. Then you can calculate the equivalent impedance just as these two in series with R1 and X1, and then in parallel with the gap of XM. So it's just like this. So the impedance is calculated this way, and the voltage is just we seen from the A and B. That's the seen from A and B. The equivalent voltage is just the voltage across A and B. So it was just like voltage divided. So the equivalent voltage is determined by this expression. It's just like voltage divided. So we are going to see how can find the torque equation of the induction motor using Thevenin equivalent circuit. According to the Thevenin equivalent circuit, the road current is determined by this equation. The road current I2. The I2 is calculated with this equation. We just see this complicated circuit as an Thevenin circuit. It's just only how the impedance as the resistance and reactance, just this. So it's equivalent. So here we can calculate the road current with this equation. And also you can calculate this is effective value. This is our point on top. It's a vector. And this I2 no point. So it's the effective value. We get this complicated equation 6.33. We can obtain this from the other equations we have studied yesterday. So eventually we get here the equation. So it's the function and torque. The torque is a function of R2 over S. It is a function of R2 over S. So this is the general equation of the electromagnetic torque based on the parameters of Thevenin equivalent circuit. So this is the equation, and this equation is important. We'll use this equation at many applications. So let's see the starting torque expression. When it's the AC induction machine, the speed is 0. So what is the torque here this time? Torque is here. We know the speed is 0, so the slip is 1. Slip is 1, so the R2 over S is R2. So we see here when the s equals to 1. So this equation turn into this equation, So the NPH is the phase number. So this is starting torque. So it's the starting torque. And also we can find the maximum torque. It's also it's about the sleep. We see what's the sleep and maximum torque. According to the maximum power transfer theorem, we have learned it in the circuit analysis theory. So we know what time we can get the maximum power transfer maximum power. So only use this equation. The real part R2 over S. Yeah. R2 over S is equivalent to the this 3 and the square root this 2 parts. So at this time the torque is maximum. We can further simplify these equations. We can simplify it. We see here. Just to get to the maximum torque, step by step. The starting torque is determined from the previous equation. After setting the slip to 1, and then we'll get the equation of maximum torque. Usually, the Thevenin resistance R1 EQ. Thevenin resistance is considered very small, very small compared to the sum of the reactance. And so our Thevenin resistance can be omitted. So the equation of the maximum torque is omitted. So this equation can be turned into this equation. So it's simplified and showing like this. So and this time we can get the slip presented here, and the reactance is equal to the R2 over S. So this is the maximum torque. equation. Now, if we take the ratio of T max over T, we can from this equation take the ratio between the maximum torque and the general torque at any speed. So at any speed, R2 over S. So it is any value. Replace we so this R1 EQ is too small. It's too small. So we can get this. We can get from this equation to this equation. It's simplified, and then can rewrite this calculator equation shown here. After simplifications, we can obtain the equation which relates the torque and the slip and any operating point to the maximum torque and slip and maximum torque. So that this is very useful equation. It can simplify a lot of calculations of the torque. If the maximum torque conditions is known without going through complex torque equations and calculations, so eventually we get this equation. So the formula is too simple. It's the function of sleep. The ratio of the two torques is a function of sleep only. So as I have noted earlier, the maximum torque is independent from the rotor resistance. However, the value of the rotor resistance determines the slip at which the maximum torque will occur. So in order to start the induction motor fast, we need to increase the starting torque. To get maximum torque at starting, we need to satisfy this equation between the rotor resistance and the reactance So this time is the maximum slip. This equation is obtained by setting Smx equal to 1 in the above equation. So in order to start the induction motor at maximum torque, we need to have R2 equal to x1 equal EQ plus x2. So this can be achieved. This can be achieved by with one rotor induction motor, because we can add an external resistance to the rotor. It can be connected outside, and use it to control and adjust the speed of the rotor. We will come back to this issue of starting the induction motor next week. So I will see link here. if we adjust the resistance and R2 increasing, so the curve vary and the maximum curve vary. So the different maximum curve. So this can be achieved by adjust the external resistance. This is set. So let's see an example. 6.3. This is also an important practice program. Let's say it's a three-phase induction motor. It also the same as 6.2. The parameters are the same. 220. Just as yesterday, we have to down the practice from problem 6.2. So, but this time we have to find the load component I2. Yesterday we have calculated the I2. So, but this time the slip is 3%. The slip is 3%. So this time, what's the torque? The torque and the power, electromagnetic power. So we have to calculate these items and B. Where to find is maximum torque and the speed and corresponding speed, and C to calculate the starting torque and the speed and the set load current. So this is a little complicated compared to 6.2 because the equations we used is complicated. 6.33, 6.36. So all these equations are complicated. But if we can find which equation we should use, it's also simple to do this problem. Let's see. So first, we should turn the circuit into 70 according to 70 theorem. So it's just like this. So we can determine the 70 equivalent voltage V1 EQ. We can calculate it and use this equation, and also the impedance can be calculated after this equation. This is the values. Okay. So just like, and then we know the slip is 3%. We can calculate the R2 over S. And also the I2, the rotor current, the I2. This is the vector and this is the effective value. It's 26. Here. Oh. Yeah, on the textbook is 26.9. It's 26.9. Ample. And also we can calculate the torque, electromagnetic torque. So just using the current, the road current, and the ratio of R2 over S. Just use this equation, we can calculate the torque. So this is also 23, and then torque and the power. Power is here. So this two is only there's only a speed difference of omega s. This is just the same.
Equal omega tau.
And then we can calculate the sleep at the maximum torque. Yeah. So use this equation. Yeah. 1.192 years. So this is use the equation 6.35. And this time the speed is easy to calculate. And the maximum torque using this equation. Just and 6.33. So just give the values of the variables. You can get the result is 175. And we also can get the three starting time. The sleep is 1. Sleep is 1. So we can calculate I2 at this time. So is 150. And also the start torque uses the equation 6.25. The result is 77.3. But here my result is 77.6. A little different. Okay. Also, we have this torque equations. So this is example 6.3, and we also have the practice problem 6.3. Also there's answer, but no the progress. So we will set this as our homework. I will give you the homework at the end of this class. Sometimes we can't understand the text, the Syria. But if we do some exercises, we can understand it easily. So we will continue to another part of the induction machine. the measurement of the parameters. You know, in our example of 6.2, let you our the value of the resistance, reactance, R1, R2, X1, X2. Let you the value, let you give us the value, but to different asymmetry. So what can we know the value of? So how can we know the value if don't tell me, if don't tell us? So how do we know that? So generally we use experiment method. We can measure these parameters and calculate it. We will discuss it on this part. So first, show the measurement of the DC resistance. We just use a simple ohm meter. We can measure the value between the two terminals. Between these two terminals, we can measure the resistance between these two terminals, and this is equal to the 2 times R1, because this 2 point is line to line, so it includes two resistance. So the resistance we get here is the value of 2 times R1. 2 times R1 is the stator resistance. So this value is twice the stator resistance. However, since the measured resistance is for DC current, but the AC induction machine, when it works, the current is alternating current, so there's a little different from this value. But usually at 50 or 60 frequency, the difference between the AC resistance and the DC resistance we measure here is not very significant. We just consider them equal. So the second text is a no load. Sorry, it's a no load test. In this test, the machine is not loaded here. There's no load on the shaft. The equivalent circuit, here, equivalent circuit, and no load is given to this one, and this time the slip is about 0 because no load, so the real speed of the rotor is we can think it equals to the synchronous speed, so the S, the slip is equal to 0. And then remember that we have resistance R2, R2 over S, here. If the S equal to 0, so the R2 over S is infinite. Yeah. So we can think here the resistance is very large, and we just think the A and B. So this circuit is open. Just think it's open because the resistance is too large. So we think it's open circuit, open circuit, just like this. So this and A and B. So this side is open circuit. We can get this simple equivalent circuit. So from the measured line to line, yeah, here the V is a line to line voltage. A line to line voltage. We can calculate the voltage, line to phase voltage divided and the state phase, the I1 can be measured from this meter, ampermeter, this ampermeter. From here, we can obtain the current I1 here, I1. So we know the V1 and the I1. We know the V1 and I1. So we can calculate the impedance of this circuit. I want to point that here because this is circuit, so the resistance is very large and the current is very small. So the losses, the rotor losses here is neglected because there's no load. It's just very small. Neglected the rotor losses. So this time there are only the losses, only the rotational losses. It's just rotating nearly the synchronous speed. There's also the rotational losses. So we can get the rotational losses using this equation. Just the P no load this NL is no load. The no load power minus the power the state losses R1 I1 the state losses. Just the difference of these two powers is we can calculate the rotational losses. So using this experiment, we can get the rotational losses. And also, here, also, we usually apply a rated voltage at the terminals, step terminals. Will measure the voltage current and the power and the power and the rotational losses. Then we calculate the apparent power S. Apparent S is 3V1 V no load I no load. Just use this equation. We have known this equation. So it's the apparent power. Using the apparent power, and the active power and the active power. We can calculate the reactive power and the Q no load. This is useful. We use the Q no load here. Q no load here. Divided by 3 times I no load square. This can calculate the impedance of this circuit. Just here, the impedance. For the reactive impedance, so it's just the sum of x1 and xm. So use the Q and the current, we can obtain the sum of x1 and xm designated by xam. So this can be obtained. We just know the sum. We just know the sum of these two reactants, but we don't know x1 or what's the x1 and xm. What's the value? We don't know x1 or xm, but we know the sum of the x1 and xm. And next, the other slides, we will use this equation, and then we can calculate the x1 or x2. But here we don't know the value of x1. We will come back later. And 3, the blocked load test. It is blocked, so the shaft is blocked here. So it takes the block. Block test. The rotor is not allowed to rotate. And just locking it. Use the mechanical method. Don't allow it to rotate. We give a voltage. Here. This voltage is gradually increased from 0 until we get the rated current here. Inside the stator. We should note that we can't directly give the full voltage, just as the rated voltage to the stator. If we do this, we will get a very high current in the circuit, because the rotor is blocked. In this situation, the slip is 0. So the R2 over S, slip is 1. Slip is 1. So the R2 over S is R2 itself. It's a low resistance. It's a low resistance. If we give a large voltage here, so the current will be very large. So we can't give a rated or full voltage. We just increase it from 0 increase until we get the rated current will stop. In this situation, we should be careful. Not to apply high voltage. We also measure the voltage, and current, and the power, So use this, we can get the apparent power. Use this equation. So it's the same as the previous one. It's the same. And we can also get the reactive power with this equation. Then the equivalent blocked reactance can be deduced by this equation. So it is the reactance part, is the resistance part. Just here, there's two frequencies. Here, this is FR, and this F blocked. The two different because the reactance of element is proportional to its frequency. So, at this experiment, we use the frequency of F blocked, but the real working frequency is FR. So we can and this here is multiplied by it. But for the resistance, there's no need to. Resistance is independent of its frequency. But the reactance is proportional to its frequency. So it should be noticed here. We can present the reactance of the circuit because R2 is too smaller than XM. So we can get the Z block, the impedance, and this equation. R2 X2 of Xm, this equation, and to get this complicated equation. Because R2 is very smaller than Xm. R2 is very smaller than Xm, so we can simplify this equation. So just the Z block can be simplified as this. It's a simplified form. This can deduce the value from the outside. And by this equation, we can get an accurate value of the circuit. So use this equation. The Z blocked is the resistance part, and the reactance part, resistance part here, reactance part here. We use the resistance of blocked, and also no load, and we'll use no load, X no load, X no load, XM, X block. So this value we all know. But this time we don't know the x1 and x2, x1 and x2, the relation of them, so we can't get the real value, but we have the some information about x1 and x2 according to different kind of motor. It have five kinds. Normally, we use the A kind. So we just think the x1 is equal to
0.5.
x2. Generally, but sometimes it's the other cases. So if we know this, we will get the x1 and x1 and x2. And then we know if we know x1 and x2, then we'll know the x1, we'll know the xm, we'll know xm. Xm is here. So how to measure the parameters? Just three steps. One, just measure the DC resistance, and second, we do the no load test. S equal to 0, and the third, the blocked load test. Just these three tests. We can obtain the parameters. The DC resistance test. So this will allow us to calculate all the performance and characteristics for an induction machine. This is a summary. You just see it. It's a summary. Okay. Okay, let's take a break. Frequency, the number of poles, and also now it's class C. We see class C motor here. For the class C, it's a high starting torque, low starting current. So it's a special kind of motor. So x1 over x2 is 3 over 7. So the relationship of x1 and x2 is here, 3 and 7. So there are several tests. One is no load test. 60 Hertz. The voltage is nearly the rated voltage. And we get the no load current, and also give us the no load power. These values are obtained from the meters, the voltage meters, the current meters, and the power meters. From the meters, we read these values. And text 2, blocked rotor, but this frequency is low frequency. It's just 15 Hertz. So the power, the voltage, and the current are listed here. And also text 4 and text 3 and text 4. Text 3 just to measure the resistance, and it gives us the R1 the stator resistance, gives us the value. And the text 4 is blocked. It's also a blocked load test, but the text 2 is for 15 Hz, and the text 4 is for 60 Hz. So the frequency is different from text 2. Also give us the voltage, and the blocked current, and the blocked power, and also give us the torque. So there's maybe some mistake on this. So this is the textbook. So here is not. Let us calculate the no load rotational loss. This is easy. If we know the input power and the current, and the static current and the static resistance, we can calculate the no load rotational loss. And also allow us to obtain the equivalent circuit parameters. So this can be done using these equations on textbook. Many equations according to different cases. This is the question A. And question B. Let us compute the torque, the starting torque, from the text form, and let's see. The solution is just from the textbook. I just explain some of it. We should notice that this four place yellow background. First is the rotational power, rotational loss. Just use this equation. The no load power minus the this is the stator losses. Because there is no load, so just use this equation. And here is voltage. Voltage is no load phase voltage, so it has square root 3. We can get this
line to neutral.
And the reactive power can be calculated using the apparent power minus apparent power. This is the active power. So the difference between them, the square. This is the reactive power.
Pythagoras triangle.
After the reactive power, we can get the impedance, reactance also here. So the no load impedance, and then to the block test, and the 15 Hertz, and this frequency we can also calculate the reactive power, block reactive power with this equation. That's this apparent power and active power. So it's easy to calculate it, and also the block impedance, blocked impedance. Blocked impedance is the sum of x1 and xm. So here we use the class C. Is the ratio is 3 over 7. The ratio is 3 over 7. So we can know the relationship between x1 and x2. So using the equations, we'll get a complicated equation. So this equation we can obtain the root because it's a simple mathematical problem. It has two roots. We use the 1.4. This is the real root. Another is that's no use. So we can obtain the x2 and then x1 and then x1. Then the xm can be obtained because the x no load impedance is the sum of x1 and xm. So if we know x1, and we also can know the xm. The equation on 58. And then using the blocked power and the state current, we can calculate the resistance, the blocked resistance here, and also the state resistance using the equation on textbook 6.56. On using this equation, we can get the R2 here. So all the parameters we have calculated them. R1, R2, XM, and B problem. So the special is here. It's we use this method just to first calculate the air power. The air power is the blocked power minus the stator losses. We can get the air gap power. Using the air gap power, we can get the start torque. Just using this divided by the speed of rotor. So it's 77. It's about the measured value. The measured value is 74. So because it should be noted that is here the so it's the double relocate motor. This is a special motor. The performance and starting and the performance and running is different performances. This is textbook 6.7. We have not put this double relocate motor. We have not put this, but the performance is special. So we calculated the torque using the air gun power. Is the air gun power is this method. That's all. It's okay. It's also the five kind of different motors. Just as the seat. This is the seat. This may be the double squeeze case because it have high starting torque and high starting torque. This is different characteristic curves of the four kinds of class A, B, C, D. Four kinds of motors. So different applications. According to different applications, we use different kinds of motors to get a different purpose. In general, the class A is used widely. Class A is used widely. This kind, this is classical. This is the classical motor. Generally, we use the class A. Okay, we have this. There's class. I will give you some homework.